The next topic is to find the endpoint with a pH electrode. Okay, usually the pH electrode is used to follow this entire titration curve. Okay? Of course, there is another method to use indicators, okay, to find out this endpoint, okay. But in order to follow the entire, the titration curve, you need to uh, have a means to measure the pH at this each point, okay. And so for the case, the pH electrode is often used, all right. Uh, if you take it on a electrical chemistry experimental course in the next semester, you will use just pH electrode and pH meters. Okay. Okay. Let's look at this figure. This is the titration curve of this material. Yeah. This is diurnal orange. This is kind of one of the indicators. Okay. This diurnal orange, it has a very complicated structure, and it is hexaprotic acid. Yeah, this is a weak acid, but hexaprotic. It can produce, okay, 6 protons, okay, when dissolved in water. Okay, how many? Which protons here? Here, carboxyl proton here, 1, 2, and 3, 4, and other 2 protons are here. What? This one, OH proton. Oh, 5, 6. So total, 6 protons can be protonated. Okay, and this is titration curve. Yeah. So nothing happened here. Nothing no seems to happen here, and then here there is a sudden increase. Okay, and then another sudden increase, and then no special thing here. Okay, and then your textbook says this one. Hmm? This is a third equivalence point, and this is the fourth equivalence point. Why? What's the first and the second what equivalence point? Where are they? Yeah. All right. What do you think? Yeah. You see, the first and second, dissociation of this compound, K1 and K2 values are rather big, okay, rather large. So it is not show any, the any distinct this pH change. Okay. Okay. Let's take an example. You know the sulfuric acid. Okay. The sulfuric acid is a very strong acid, but it deprotonates in 2 steps. All right. And when you titrate sulfuric acid with a strong base like sodium hydroxide, how many equivalence points do you expect? Since it dissociates in 2 steps, you may think, oh, we'll find 2 equivalence point or endpoints. Okay, but actually you will see only 1 equivalence point. Why? Because the first dissociation constant is almost infinity. Okay, so it is not shown in the titration curve. Okay, so you will see only 1 equivalence point. Okay, likewise here in this case, the general orange, the first dissociation maybe here and second one maybe here, they are the K1 K2 are large, so it is not clearly seen here. Okay, only third and fourth one. Okay, okay, and third equivalence this reaction is this one. Here H6A, it already lost 2 protons, and the starting form is 1, H4A2 minus, okay, and reacts with a strong base, and it becomes this one, this species, and then this species now reacts with this hydroxide ion, becomes this one, okay, and then this one should react with hydroxide ion to lose another proton and then another proton, but here um, fifth and sixth dissociation constant is too small, so it is not seen in this titration curve. You understand? But how do you know this is third and fourth? Yeah, yeah, we can know from this titration curve. Okay, look at that. Third, this equivalence point. What's the volume here? If we follow here, and this is a 90 microliters. Okay, and then fourth equivalence point, you have to add 120 microliters. So the difference is what? 30 microliters. Okay, and then since I said the first and second equivalence points are not seen here, but actually the first one is around here. Yeah, here. Third, 30, because this one difference is 30 microliters, 30 and 60 and 90 and 120. Okay, so although it is not seen, but they are here. All right. So the distance the volumes of sodium hydroxide to reach each equivalence point are all the same, 30 microliters. Okay, so from this the volume difference, we could infer, oh, here this is the first one and this is the second one, second equivalence point. All right, yeah. But here the topic is finding the end point. What's the difference between end point and equivalence point? You see, equivalence point is the theoretical point, but experimentally we find the end point. Okay, now we simply assume this end point is very close to the equivalence point. All right, so this end point is experimental point. Okay, here. Well, how to find this the end point here? Yeah. Maybe graphically. hmm, Once you get this very nice titration curve, and then you can directly read from this curve, okay? Because at this equivalence point, yeah, the pH change is a maximum, okay? And then equivalence point around here and there, okay? But mathematically, uh, we differentiate this curve, yeah? And then we can get a maximum, okay, here at the first derivation, yeah? So you differentiate this one. How to differentiate this discrete form? Okay, this is not continuous because you know, there is no data between these two. Okay, but since this is we can say, oh, although this is discrete, but maybe no problem to get a differentiation, because we take difference. Okay, each points here. Let's look at this table. The first derivative, yeah, look at that. Let's start here. 85 microliters of NaOH was added, okay, and then pH at this volume 4.245, okay, and then you add 1 microliter, okay, and then pH increased this amount, and then here you take the difference, yeah. Mathematical differentiation is not possible because it is not continuous, okay. And then here, first the derivative, um, you take uh, the pH change per the added the volume, okay, here. All right, and then you do this process, through maybe from 85 to 96, okay, 96 here around, yeah, for this third, this end point, yeah. And uh, the next the difference, what was the volume of the added sodium hydroxide, yeah, since this is 85 and this is 86, yeah, the volume, yes, you take the middle volume, okay, which is 85.5, okay. The pH change is what? 0.155. Okay, this is a pH um, change. Okay, per 1 microliter volume change. Okay, and then you do this kind of calculation. Okay, here, and then you got this one. All right, and then you take the maximum point here. At this maximum point, that is the end point. Okay, here the maximum value is this one, 0.340. Okay, and then what's the volume there? In the case, this is 88.5. Okay, so this one is the first equivalence point here. All right, of course, this is not absolutely exact, because anyway, you added volume, uh, one microliter change. Yeah, so in order to what find more the end point more accurately, you have to add, 80, for example, 85 microliters of NaOH, and then maybe 85.1 and 85.2, yeah, like that. But that takes too much time. So 1 microliter change may be all right. Okay, but error must be cannot be avoided. Okay, yeah, this is one method. And what if you differentiate one more, this is the first derivative, and what about the second derivative? Okay, so the maximum at the maximum point, yeah, when you do the differentiation one more, and then this maximum point becomes 0. Okay, here. So if you get the second derivative, and then you find out the 0 point. Okay, 0. And 0, this one, at this 0 uh, point, that's the equivalence point here. Okay? And again, you take this pH difference here. Okay, and the pH difference here is what, 0.0710. Okay, and then what's the volume in the case? Yeah? In this case, you get you take this one, 86 microliters. Okay, yeah, like that, and then you have these values for the second derivative. All right, but here there is no, yeah, no 0 point here. Okay, no 0 point, because yeah, they are all discrete. You have some positive point here, and then it decreases, and then it crosses 0, and then uh, it becomes a negative value. Okay, so you make a graph out of this table here. Okay, now this is second derivation. The x-axis is added, added volume of NaOH, and these blue dots are the second derivative values. Okay, and mm, they have positive values and negative values. But if you draw this curved line, and then you can naturally this line cross this zero line. Okay, here. Okay, and then you read from this uh, graph. Yeah, this 0, and then oh, this is 88.2 microliters. Yeah, that's the first end point or equivalence point. Okay, let's compare. In this case, the first derivative, you got 88.5 microliter, and that's the first equivalence point or end point. But from the second derivation, you got 88.2 microliters. Yeah? There is some difference. Okay, some difference by 0.3 microliters. Okay, but that's inevitable. Why? Because although these titration curves are very nice looking, but actually there is volume change is 1 microliters. Okay, so that's why, that's the error source. Yeah? To make these volumes close each other, and you have to add know the not this one microliter interval, but you add the more, the little by little. Okay, maybe you want to add 85.1 and 85.2, like that, and then you can have these two values very close. Okay, likewise, you do the same thing for this force, this equivalence point, and then you get this the second derivative curve. Okay, here also this one, these points now pass through this zero. Okay, and then you read from this curve. Yeah? That's how you find the end points. Okay, yeah, this is the as I said, I already mentioned this one. Okay, this pitch change with respect to volume. Then here you take the volume difference, and then you also take the pitch difference. Okay, and second derivation here, for example, this is the second derivation, the pitch derivation for the first derivative, and then this difference is what, 0.071. Yeah, all right. And then what's the um, volume change here? 86.0 minus 85.5. Yeah, here this one is from this volume. Okay, and then this one is from let's see, actually from this one, this volume. Okay, so volume is what, this one, 85 point, not 0 but 5. Okay, that way, yeah, you can construct these second derivative graphs, and then from this graph you read this one, crossing point here. Okay, actually, but uh, first derivation may be all right, but the second derivation, if the second derivation is not very nice. Okay, this is quite nice data, but as you do the derivation more and more, and then the error introduced more severely. Okay, so I think maybe the first derivation may be enough, or if you want, you can directly read from this raw data. Okay,